We now move on to the third talk of this session. The title of this talk is Conditional Abstraction Trees for Sample Efficient Reinforcement Learning. The talk will be presented by Mehdi Dadvar.
Hello, everyone. My name is Mehdi, and I'm with Arizona State University. Today, I'm going to present our paper titled Conditional Abstraction Trees for Sample Efficient Reinforcement Learning. Reinforcement learning algorithms in general are capable of solving a wide variety of problems formulated as MDPs. In a sparsely bought setting, their scalability could be really limited. So here we have the example of the office board. So in the office board, we have the robot, we have the coffee place, we have the mail place, and we have the desk. And the coffee and mail should be delivered to the desk. And in this setting, we studied the performance of PPO, a well-known state-of-the-art deep reinforcement learning algorithm. And as you can see here in the results, as we increase the complexity of this problem, by increasing the size of the problem, the performance of PPO drops significantly. And this suggests a scalability issue in reinforcement learning algorithms and can be generalized to a variety of other algorithms. So what would be a solution? I think we lost the slide.
Back up in the meantime, I need to. We lost the camera. It will be back momentarily.
Okay, that's fine.
Sorry.
Oh, it's okay.
They can still see your slides, so if you want to keep going.
I think I would need my slides.
Yeah. They can't see your slides on the Zoom meeting, but we just can't see them in the room as well.
Yeah, thank you for being patient. So yeah, reinforcement learning algorithms are susceptible to scalability issues. And we have studied that in the office board for PPO. And as the results suggest, as we increase the complexity of this domain, the performance of the PPO drops significantly. So what would be a good solution to solve this? State abstraction, actually an effective and good.
Let me just read this one. Yeah.
So a state abstraction in general can be perceived as a map, the original representation of the problem to a reduced size representation of the problem. And we can define our abstract MDP derived from the original MDP. But here we have the abstract states. So we have the abstraction function phi that maps the abstract states, maps the concrete states to the abstract states. And using our abstraction function phi, we can define the abstract transition function and the abstract reward function. Although having these definitions in hand, we can better define the state abstraction, the general notion of a state abstraction, but the specific approach taken to construct these abstractions actually impacts the benefits that an RL agent can derive from it. So now we are going to take a look at some of the properties of a state abstraction. In general, there are two main paradigms of a state abstraction, bottom-up and top-down abstraction. In bottom-up abstraction paradigm, one may start with concrete states and incrementally merge concrete states to construct abstract states. And this process often involves computationally expensive operations to find the similarities in the concrete states. For example, leveraging the topological similarities in the state transition graph. So because of that, constructing a state abstraction using bottom-up approaches may suffer from a scalability issue as well. And that defeats the purpose because we wanted to address the scalability issue. On the other hand, in top-down state abstraction, one may start with an initial coarse abstraction and progressively refine that coarse abstraction. Using the abstraction, building the abstraction using top-down methods could be relatively more scalable compared to the bottom-up approaches if it is synthesized with a purely abstract reinforcement learning routine. Although the idea of top-down abstraction has been studied in the literature, but no existing work has tried to synthesize abstraction refinements with a purely RL, abstract RL routine, like independent from working with concrete samples. And that is the motivation of our work. So a question is, what is a good abstraction, in fact? Intuitively, a good abstraction should give us more details around the informative and salient part of the state space, and it should be coarse otherwise. On right, we have on the top two pictures, we have two different states of the taxi board. So the taxi board is another a common domain for evaluating reinforcement learning algorithms. So we have two passengers that have to be picked up one by one. We have the taxi and we have the building, which is the destination location. So using this intuitive idea of the good abstraction, on the bottom, we can see the corresponding abstractions for our concrete states on the top. So for example, on the bottom left, the goal of the taxi is just going to pick up the orange passengers. Because of that, we have more details around the location of the orange passenger. And on bottom right, the orange passenger has already been picked up, and the goal is just dropping off the passenger into the drop-off location. So because of that, we have more details around the building. This idea, this intuitive idea of good abstraction implies that abstraction on one state variable should be contingent on the values of other state variables. And that explains the idea of conditional abstraction. Our method, CAT-RL, learns these conditional abstractions in the form of conditional abstraction trees while doing a purely abstract reinforcement learning. So here I'm going to use another example in this domain called Wampus board to explain the overall procedure of CAT-RL. So Wampus board is pretty easy. We have the agent and we have the goal location, and we have also a pitfall to avoid. And the state of this domain can be described using two state variables, X and Y, denoting the location of our agent. And we also know the range for each state variable. So in this case, it's going to be 1 to 4 for both of the state variables that we have. As a matter of fact, partitioning these ranges of state variables is one way to construct abstractions. If we do that, so for example, if you break down the range of each state variable into 2, we can get a very coarse abstraction on the bottom, as you can see. CAT-RL starts with a coarse abstraction, and this example could be like a good coarse abstraction to start with for the CAT-RL. So we can let the agent to interact with this coarse abstraction and to train an abstract policy. However, we probably know that this abstraction is likely to be too coarse, and we need to refine that. So how do we do that? We need to fix the policy, first of all, and then we need to let the agent to interact with this coarse abstraction, and we collect the abstract transitions. And then we can use a specific metric to identify the unstable states. So if we do that, as you can see here, the MDP model of this Wampus board, probably S bar 1 and S bar 4, the gray and the orange abstract states, are going to show some instability. How do we capture that? we use the dispersion of temporal difference error as the metric to identify unstable states. So here our unstable states are going to be S bar 1 and S bar 4, and then we can define them with respect to one or more state variables. And as a result, we can get a more refined abstraction, which has more details around the peak location, around the goal location. So now that we know the idea of conditional abstraction, we can discuss a mechanism by which we can store, expand, and interpret these conditional relations between abstract states, and we call that conditional abstraction trees. So now we are going to review the very same refinement process, but now I want to visualize the expansion of conditional abstraction tree to get a better idea of that. So on the top right, we can see the root node of the cat or conditional abstraction tree, and the root node only contains the original range for each state variable. And so since we only have one abstract state here, that is going to be our unstable state. Not really hard to find that at this point. And then we need to define what state variable should be blamed for this instability. Cat RL considers all the possible refinements and chooses the one that creates new abstract states with minimum dispersion of TD error. So if we do that, and we can refine our initial course abstraction, we get an abstraction like that. And then we can again let the agent train its abstract policy at some point. We need to refine. So we need to evaluate the abstraction. We find our unstable states, and we keep doing the refinements. This process can continue. And as we continue the learning, evaluation, and refinement phases, we get more details around the salient part of the state space, and that's what exactly what we want. CatRL needs to dynamically regulate these phases to effectively synthesize the abstraction refinement process with the learning and purely abstract policy, or just by implementing purely abstract RL. So in the learning phase, in general, we need to employ a reinforcement learning algorithm. And in this paper, we just employ the vanilla Q-learning, the most fundamental algorithm that we can use. But instead of learning the policy over the concrete state space, we just learn a policy over the abstract state space. And then continuously, our agent checks the refinement condition to see if it needs to refine the current abstraction. We set the refinement condition to be to check if the recent success rate of the agent is below some threshold. So as long as that is the case, the agent, like after certain number of episodes, checks that condition. And if the success rate is below that threshold, it means that we need to refine our abstraction. So we initiate the evaluation phase. In evaluation phase, first of all, we fix the policy, but actually it's going to be, other than that, it's going to be the same RL routine, but the policy is fixed, and then we collect the abstract transitions. And we do that for a specific number of episodes, and that could be one of the hyperparameters of CatRL. Once that is done, we can identify the unstable states, and then the evaluation phase is done, and then we can initiate the refinement phase. And the refinement phase, as we already know, the intuitive idea of finding a contributing state variable for instability, we can find those state variables, and then we can refine the cat accordingly. And after that, we can start a learning phase again. And this process can go on and go on until we are happy with the abstraction, until we are happy with the success rate of our agent. We conducted our empirical evaluation on 3 discrete domains and 2 continuous domains. We actually adopted significantly larger instances of these problems in stochastic settings, except for the mountain car, because it comes with the fixed setting. And as you can see here, as the results suggest, a vanilla Q-learning has been able to outperform state-of-the-art reinforcement learning algorithms in all of these domains, as a result of the improved sample efficiency under CAT-RL. We have actually the results of the original Q-learning, and we can see that the original Q-learning is actually, it is performing really poorly in these domains. But when we construct effective abstraction, then we can be able to boost the performance of the vanilla Q-learning and outperform, for example, PPO or A2C or even DQN in these domains. We also conducted a scalability study. And here we did that for the office board, and we adopted different instances of the office board. So on the far left, we see the smallest instance of the office board, and on the far right, we see the largest instance of the office board. PPO and Q-learning failed to scale with the increasing complexity of the problem, but CAT-RL has been able to show relatively higher degrees of scalability. One may ask about the runtime of our algorithm, and that would be a fair question, because on top of all the regular reinforcement learning computations, we're also doing a lot of computations for constructing conditional abstractions, for refinement of the conditional abstraction, and so on. The results are quite surprising for us as well. So for the small instance of the office board, for 18 by 18, for example, we can see that the vanilla Q-learning without CAT-RL is the fastest approach and completes before all of the other methods. But as we increase the complexity of the problem, we can see that CAT-RL becomes the fastest method amongst all the other baselines that we are evaluating. So to wrap up my presentation, I'm going to review some of the main concepts of this method. So CAT-RL basically learns the conditional abstraction trees on the fly while doing reinforcement learning. And as a result of that, a vanilla Q-learning has been able to outperform some of the well-known baselines as a result of improved sample efficiency. And also, if you refer to the paper, we have more results regarding some properties of the abstractions that CAT-RL constructs. So for example, CAT-RL learns some abstract representations that can draw out some similarities across the state space. And last but not least, we know that running the reinforcement learning algorithms could be sometimes a taxing job because of tuning the hyperparameters, especially for deep reinforcement learning algorithms, but that is not the case for CAT-RL. First of all, CAT-RL has a few hyperparameters, and second of all, the performance of CAT-RL is not too sensitive to the values of these hyperparameters. As long as those values are not set to drastically large or drastically small values within their ranges, CAT-RL performs robustly against that. My last statement, the main message of this paper is not to show that CAT-RL necessarily is better than like deep reinforcement learning algorithms, although the results showcase that. But the point is, by constructing effective conditional abstractions, we can address the sample inefficiency problem of the reinforcement learning algorithms. Thank you so much for paying attention, and I'm looking forward to the questions.
Thank you, Mehdi. I now request Bingxiang Hu to share her thoughts on this paper.
Thank you for the presentation. It is a nice paper. So I have I'm Bingxiang Hu. I'm from University of Alberta. So this paper proposes CAT for solving the challenging deep reinforcement learning tasks. So the key idea behind CAT is to split the action space in a dynamical way based on some of the state variables. So CAT-RL has demonstrated its excellent practical performance. So I have two questions. So one is mathematically, is there any deep connections between the CAT and also the linear functional approximation in RL? And the second question is, when you're doing experiments, so have you ever compared the practical performance between the optimal policies for the concrete MDP and also the optimal policies for the abstract MDP. I mean, to see whether the abstract MDP is a good approximation of the true concrete MDP. So that's all my questions. Thank you.
Thank you for the remarks and for the thoughtful questions. So about the relation between CAT and linear function approximation. So basically, CAT is a representation of the word, an abstract representation of the word. And we showed that CAT-RL algorithm can actually synthesize the interaction between our function approximation and the abstract representation of the word. So in that sense, yes, there is a relation, but the relation is algorithmic. And regarding the second question, that's a really interesting question because again, one may ask, okay, so we built these abstractions. So is that still like all the Markovian properties, do they hold still? And that is one of the topics of our future work that like in the ongoing project, that we need to exactly compare that property, the Markovian property of the abstraction, the abstract MDP. But in general, yes, so in the results, we had the performance of the Q-learning agent without CAT-RL stuff over the same domains. So in that case, yes, we have compared the sample efficiency and also the runtime of Q-learning over the concrete representation of the environment compared to the CAT-RL, which does the same thing over the abstracted data space.
So do we have any questions from the audience?
Thank you for the interesting presentation. Actually, I had just one question about like you applied the Q-learning algorithm in the abstractive space, basically, as I understood. How sensitive is it? How sensitive your approach is to the choice of the RL algorithm? Did you try any others?
Yeah. So thank you for your question. So basically, we synthesized one reinforcement learning algorithm with the constructions of these abstractions. We have not studied CAT-RL with other choices of reinforcement learning algorithm, but to make sure that this study is a fair study, we went for the most fundamental choice, vanilla Q-learning. But in general, the idea of CAT-RL can be applied to a broad range of reinforcement learning algorithms, including some of the deep reinforcement learning algorithms as well. But depending on the nature of the underlying reinforcement learning algorithm, we might need to deal with some nuts and bolts and some engineering stuff to make it work with this approach. But theoretically, it should be compatible with a broad range of reinforcement learning algorithms.
Hello, thank you for the very interesting talk. I'm trying to without having read the paper, I'm trying to understand a little how this looks in a more abstract way, in the sense that here you have shown aggregation of states, but the actions remained essentially the same. So it was a very simple rule to go from concrete actions to abstract actions. What is how would you define it in a more general context where you have to also think of abstract actions, not just abstract states?
Thank you for your question. So you're right. While we are doing a state abstraction, necessarily we have to deal with some notion of action abstraction as well, because state abstraction induces action abstraction as well. So in this work, we were not really concerned with specific methods for action abstraction, but instead we went for the idea of extended actions, which can be defined as abstract actions, but very trivial choices of abstraction actions. In the sense that, so on the concrete level, we might have for example, for the bump sport, left, right, up and down. So the extended version of that action is going to be taking that action continuously until we reach a new abstract state. So we had the idea of abstract actions, but we went for a very trivial choice because we wanted to study the benefits and complexities of the state abstraction. But one of the benefits of CAT-RL could be generalizing options across the abstracted data space. And that's one of the, I would say, promising future directions for this work.
The remaining questions, I think we can ask offline. So let's thank the speaker, Mehdi Dadvar and Bingshang Hu for the wonderful thoughts. Thank you.